All right, how's everybody doing? Good weekend? Ready for fall break? Yeah? Okay. All right. So, just to update you on where we're at on things. Last class, Challenge 2 was supposed to be released today, but they're actually going to release it on Wednesday. It's still not due until the 18th, though. So you'll see that appear on Canvas, I think at like 8 a.m. on Wednesday. You'll see the post about that. Just to give you an idea of what that assignment actually will be. So the main things that you'll have to do, first you're going to have some code for both stacks and queues that I'll provide to you on Canvas that will have everything that the TAs are expecting. And so what you'll need to do is add a display function to the stack class that's able to show the contents of the stack and without, like actually popping everything out of it or whatever. So that will be one thing you add. And then the main thing that you'll do is that in your demo, you'll bring in your stack code and you'll modify it to become a queue rather than a stack. And so if you remember stacks and queues, I know it feels like it's been a while. So with the stack, we kind of just had like these few main functions that we use. So you could push something on, you could pop something off, or you could peek and look at something that's on the top of it without popping it off. And so the way that was implemented is just using linked structures, so pointers. And so, for example, we would just maintain in our stack, the one thing that we keep track of is the top of the stack, right? And so, for example, when we would add something to the stack, what we would do is simply make a new node for it, and then we would set our current top to point its next pointer to point to the new thing we're putting on the top, and then set that as the top. So pretty simple operations there. And this code is, all of 50 lines to do a stack. So not too bad. And then,
is this the code that you're going to give us?
Yeah, this is the code I'll give you. I'll probably add a few more comments to it just so it's clear.
You said you're giving us a Q code also?
Yes, I'll give you Q code as well. But for the actual challenge, you'll just bring the stack in and you're going to modify the stack to have a queue-like behavior. So you won't have to write a separate class or anything to do that. They will just have you change what's in stack so that it no longer behaves like a stack.
And we can learn that by referencing.
Yeah, by comparing these. So if you look at, when we push onto the stack, we set our top to be that new variable. Now with a queue, the same thing. When we push onto it, rather than the top, we're using the last element. So first and last for the queue. And so it's really not much of a change at all. It's a couple lines. But yes, I will give you, so pretty much everything that's in this folder that you're seeing here. So we have our really, really basic node class that's just, every element, and it's just got a data field for an integer and then the next pointer. And we use that, so in Q, we have a first node and a last node, and then we have our operations of push, pop, peek. And then in a stack, we just have a top pointer, a top node, and then the same operations. So you'll get that, and then the headers and the actual implementation of these, as well as kind of the test code and what the output should be there. And so on the assignment itself, I believe it will be, I'll make sure that, let's see. It looks like this is the same. I will go through this though and make sure, since it's been updated a little bit, that like the test code that I give you has exactly this test code that you'll be using in your assignment. And then there's the example output. So overall, this programming challenge should be a little bit easier than like the linked list, I think, especially like now that you've done linked lists, right? This is a little bit better, but definitely, I think get it done earlier rather than later. You have a little bit of extra time if you want, just because it'll be released on Wednesday. And reminder, we will not have class Wednesday, and then you're on fall break Friday. So we'll be back on Monday here. And I think that is pretty much our logistics for the next 2 weeks. And we'll do AVL trees today, we'll do AVL trees a week from today, and then we'll do heaps. And that'll kind of seal off what we'll have on our next exam. Questions on any of the scheduling stuff? Cool. So last time, you remember we were implementing a binary search tree. And just to remember, the binary search tree is just this nice tree structure where each node has up to 2 children. And we follow this idea of, when we're looking at the tree, everything to the left of a node is less than it, and everything to the right is greater. And we just continue that down, and we can consider each node its own subtree and apply that principle. And so we've been doing that for a while now. And then there's your very basic example of something that is a binary search tree and something that is not a binary search tree. They're both binary trees, but only one is a binary search tree. And we were building that in C++ with these methods and these files. And you'll use these not on, so the challenge you're about to do is stacks and queues. The challenge after that, which will be a couple weeks, will be using the binary search tree stuff. So we will wait until we get closer to that, and then we'll kind of review this code again so that it's fresh in your mind, and with the context of what you need to do in the challenge with it. But today we're going to start talking about AVL trees, and we'll kind of stick today to just the concepts. We won't do like any implementation, any code, because I feel like you'll probably forget everything we do today anyways. And so just try to kind of get it primed in your brain somewhere so that when we come back a week from now, you'll kind of recall the general concepts, and we can start getting into it in greater detail. So what is an AVL tree? So first of all, what we need to kind of think about here, we've been talking about binary search trees for a while, and like, why is a binary search tree such a great thing? And here is a basic example of that. So let's imagine that we have 2 different data structures, the same data. This first one, it's just an array or a vector, and we've got the numbers in this order. And let's assume that we have a binary search tree, same numbers, and they've been inserted in such an order that this is what was given to us in that tree. So now the basic thing you can do to compare these is to say, okay, if I need to search either of these data structures, and I need to search them, so I'm calling find 90, right? So thinking about how we would do that, just in the most naive approach here. So if we've got this array, we could just start at the beginning, right? And check each element to see if it's 90. And if we find 90, then we return 90, and we say we found it, otherwise false. Same thing for the tree, right? We can traverse the tree and look for 90. But you can see there's a major difference here, right? and the number of comparisons that are required. And the reason is because this tree has this really nice property of every time we do a comparison, we kind of cut it in half, right? And so when we're thinking about like our big theta, in terms of n, here n is the number of elements, so either the nodes or the elements in the array. We can see that in this case, if we compare these, the tree performs much better, and it performs at a big theta of log n. Now, in both cases, we should always think about the worst case possibility here. So this isn't truly the worst case. The true worst case is that the element's not in the structure at all. So you can add one to each of these, to say that this element's not there, like if we were looking for 100 or something, right? You would still do less comparisons on this tree. But it's kind of a contrived example because the order in which these elements were put into the data structure matters quite a bit here. And so this is not really the true, so for these two structures, this is the worst case. But for the more general concept of these structures, this is not the worst case tree that could exist. This is the worst case tree that could exist. Okay, so imagine that rather than having the numbers in the convenient order we had before, right, where when I built my tree, I got this very nice kind of balanced looking tree. If the numbers came in this order, right, in a sorted order, and I insert them into my tree, I'm just going to keep putting things to the right because it's larger, 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 larger. So now, there's no difference between the two structures, right? If I'm looking for 90 in either of these structures, I'm going to do the same number of comparisons. And so we've lost all the benefits that the binary search tree has. And this is a valid binary search tree, right? It follows all of the rules. It's just unfortunate. And so to really make use of trees, or binary search trees in particular, we've got to make sure somehow that this doesn't happen. And we've got to do that with a computational complexity that is not significant, right? So it can't cost us more to make that structure correct than it would, to just search through this array here. And so, well, you'll see this called making the tree balanced. And that's kind of intuitive because you can look at this tree versus this tree, and you can say that these are pretty balanced. Or the first one's balanced, this one's not balanced, right? If you were to take the tree by the middle element, pull that up, and then those were to fall down, now it's getting more balanced. But not truly, you need to kind of fill it in as well. And so when we talk about having balanced binary search trees, that's what we're talking about. And in general, we call them self-balancing trees because the idea is that we want to maintain the balance as we add things. So the balancing operation happens kind of at the insertion step. So every time we insert something, we ensure that the tree is balanced. And that limits us from having to iterate through the whole data structure to balance it at a later point. So we're going to talk about AVL trees. And AVL trees are named after two people. They were Soviet scientists. I think one was Israeli as well. This is one of the earliest examples of a self-balancing tree, and it turns out to be pretty good. It turns out to be pretty much as good as anything else afterwards, with the exception of very particular use cases where you need to access things at a certain frequency. There are plenty of other types of self-balancing trees. AVL trees are probably the simplest approach in terms of implementing the code and thinking about it. And they're also, very efficient. So they are pretty much what we study when we look at data structures. There are other types you will hear, like red-black trees are a type of self-balancing tree that maintain some properties similar to this. They're a little bit more complicated to implement. And there are a whole list of these. But so AVL trees are kind of the fundamental self-balancing binary tree, and that's what we'll look at in this course. And so the AVL just stands for the names of the people who created it. So the basic idea of an AVL tree is that we can look at the heights of the subtrees that exist for any node. So if we have a node, we can look and see for its children, which does it have one child that has like a bunch of nodes and one that just has like one or none, right? And kind of intuitively, you could say well, the further apart those are, the less balanced this thing is. And so what we want to do is we want to make sure that the left and right subtree of any of the nodes never have more than a difference of 1 in their heights. And so to do that, what we do is we compute something called a balance factor for each of the nodes. And this is what tells us if we need to take a step to balance the tree or not. So the balance factor, it can be defined a couple of ways. For our course, we will define it as the height of the left child minus the height of the right child. That's kind of an arbitrary choice. You could use the height of the right minus the height of the left. You just got to be consistent with how you do it. And for us, we will say that if a left or right child is null, so there's nothing there, that will be considered a height of -1. Again, that's a choice you can make. Some people use 0 there. It doesn't really matter as long as you keep it consistent throughout the tree. And so, just to kind of keep it in mind, the height of null is just -1 when you're doing this. So here is a basic example of how we would compute these metrics. So when we're talking about the height of the node itself, you can see, so the height, if you remember from when we first talked about trees, is the longest path from the node to another node. So if we just look at 50, right, the longest path to another node is 2, right? Because you go to 60 and then you can go to 70. So that's how to think about the height. In a similar way, 60, you can go to 70, that's just 1. 70's height is 0, and then the children of 70, they're -1 in the way we're doing this, because they just don't exist, they're null. So if we look at the formula that we've come up with for a balance factor, we're looking at the height of the left child minus the height of the right child. And that's going to give us our balance factor. So let's start down at the bottom here, because we'll be doing this as we insert nodes. So we will build the tree and keep it balanced the whole way through, right? So when we're thinking about doing this, we're only really considering what we've just added to the tree, because we assume the rest of it has already been taken care of as we built it. So if we look at this node 70 here, and we look at the height of its left child and the height of its right child, well, they're both null, which we decided would be -1, right? And so that gives us -1 minus -1, -1 plus 1, and gives us a balance factor of 0. And if you remember, we said as long as the balance factor is not greater than 1 or less than -1, we're okay. We consider it balanced. So if we go up a level to the 60 node here, so it's got one child, right? It's got a right child, 70, and then it's got null here for its left child. So that gives us -1 and then minus 0 for the height of the right child. And so we're just getting that 0 from here, height of 70. And so when we add that up, we get minus 1, minus 0, so minus 1. So that node is okay. It's not less than -1, and it's not greater than 1. No problem there. So when we get up to this root node in this case, now we have its left child is also null, so -1. Its right child is 60, which is a height of 1. And so that gives us -1, -1. And that gives us -2 as the balance factor for 50. And so that's outside of the range. And with this example, you can see how to make this tree better, right? How would you make this better?
60 on the other side, and reconnect the 70 to the 50.
So yeah, you can just pull 60 up, right? And then you can put 50 to the left, 70 to the right. Pretty basic. And that is in fact what we'll do here. So just to be thorough with this, so we did a tree that's going this way. I'm going to do the same tree that's going this other way, just so you can see that the math is the same. It's just the sign is flipped, as you might expect. So same thing here. You've got -1 and -1. Gives you a balance factor of 0, and then 1, and then 2 instead of the -1 and -2. And the same way of fixing that. So, since we know that we need to change here, we essentially want to do this, right? And what we're going to call this concept of changing a tree like this is a rotation. And the reason we're going to call it a rotation is that it can be convenient to think about rotating around a particular node that you're targeting. And so we'll have a few different types of rotations that you can do to balance the tree. And so in this case, this is what we would call a single left rotation to get from that to that. And you can kind of imagine that rotating to the left with 60 coming up to the top. But again, this is just based on computing these balance factors and altering the tree to make them fit back within range. So I'm going to go through a couple more examples that are a little more, we'll get progressively more involved as we go, because it's not always as easy as just having like the 3 nodes there and doing that. So we've got this tree here, binary search tree. And you can see we've got 60 as our root, 50 and 70, 40, and we're going through some insertions here. And so at this point, if we compute the balance factors, this tree is fine, right? There's nothing we can do to this tree. And this is kind of nice when the trees are small, just to look at them like this. Like, is there anything you could do to this to make it more balanced? No, I mean, you think about moving anything around here. There's not a configuration that provides you with more balance. So this is fine as we're building this tree. Okay, so let's go ahead and insert 30 into this tree. And when we do that, this is where we get a tree that has a balance issue. So we've added 30, which puts it down here. And so these are balance factor computations, and I won't make us work through them every single time. But you can see them 0, 1, and then 2 is the problem here. And so...
So wasn't it a problem before we added 30 then?
No. Because if you compute it, you got to remember that when nothing's here, right, these are the negative ones. And so 50's balance factor is 1 at that point. When you add this node, now it changes it. It becomes 2 because this propagates upward.
So 50 has 2 children then?
So its balance factor is 2, and that is based on the fact that it has its left child has a height of 1, and its right child, which is null, has a height of -1. And when we put that through the balance factor calculation, 1 minus minus 1 gives us a +2.
But
And
before we added the 30, it had a height of.
so before we had added 30, then this one, height was, like this. So its balance factor was 1 at that point.
The 1 minus 0.
Yes. So the main thing being that as we insert nodes into a tree, right, and we look at these balance factors, the node that has the problem is not going to be necessarily the node that you've just inserted or even its parent. In fact, the grandparent, if you want to think of it that way, is usually where you're going to find the balance issue. So what we can do to remedy this is, in this case, what we would consider a right single rotation, which is a little bit of a spoiler alert that these are single rotations. There may be some other types of rotations in the future. So what we can do is perform this right single rotation on 50 and get some better balance factors. So I'm just going to cut out what the tree was here so you can see that as a reference, and we're going to work more closely with this portion of it. And so what you can see is we've got 60, 70, 50. You can map those how they were in the tree. And what happens after this single right rotation around 60 is that we are going to end up with this structure like this. So instead of that kind of structure, we'll end up with this. So this is how the tree will look once we're done. And if you compute the balance factors here, you're fine. The tree is balanced again. So just to compare them, go from having 30 right below 40 and to putting 50 right there under 40 as well. So you can see how that has made this tree more balanced just visually. So let's look at continuing with this example. So we've rearranged it to fix that one, and we use the single right rotation for that. This time, same tree, right? We're now going to insert 20 into the tree. So following binary search tree principle, we start at the root. Okay, 20 is less than 60, it's less than 40, it's less than 30. 20 is almost here, right? And so now we start to compute our balance factors. 20 is fine, 30 is fine, 40 is fine. But now, actually the root of the tree, 60, has a balance factor of 2. So that's a problem. So we need to apply a rotation to fix that. And so what we're going to do is, remember we had 50 here. So what we can do is take and make 40 the root of the tree, and then move 60. So we're going to grab 40, putting it up here. 60 is coming down here. And then what we're going to ultimately run into once we do that is that 40 already has a right child, which is 50 here. And so we need to be able to do something with 50 because, as you can see, right, we're grabbing this and moving it, and there's 3 lines, right? And so when we do that, it's binary search tree. So we can only have 2 children, ultimately. And in this case, 50 is kind of this third child that's not going to work for us. And so we have this, and we have 50, and the question is what to do with 50. And it's not actually a hard answer. We just follow the binary search tree principle, and we put 50 where it fits based on traversing the tree as it is after we changed it. And so it becomes the left child of 60. And now when we compute the balance factor for this tree remains balanced. Okay, so we've had a tree like this. We're going to go ahead and add 45 into this tree. And so 45 is greater than 40, it's less than 60, and it's less than 50, so it comes down here. And as we compute our balance factors, we can see this tree is pretty good. Nothing to do here. It's fine. None of the values are out of range. So now, let's go ahead and insert 48 into this picture. And so we come down, we place 48 exactly where it needs to be placed for binary search tree. And we start computing our balance factors up the chain. And we find that, in this case, 50 has a balance factor of 2. So that's not going to work for us. And so we need to do a rotation to restore this balance. So
We start at the bottom, so like number 48.
Mm-hmm.
So why is it -1? Like why is -1 minus -1?
Yeah, so it's so the formula for the balance factor is the height of the left child minus the height of the right child. In this case, it has no children.
So it's both negative.
They're both -1, yeah.
So then you take that answer and plug it into.
And that becomes, that's the balance factor for this node. And then you just do that for each of these nodes. And you really, because of the way that we build the tree, the only path that is affected is the path that you traverse to insert it. So you don't have to redo the whole tree or anything.
So for 50, you got 1 that's -1. I mean, the -1 comes from the 45.
So the -1 comes from it doesn't have a right child.
So what does 1 come from?
So the 1 comes from the 45. So the height of 45 is 1. And this is a distinction that matters, and I do find this to be a little bit of a confusing notational issue. So you have to remember this is the balance factor, not the height. The height is how many steps does it take to get to kind of like a leaf node. And so for 45 it takes 1 step, so it's 1. For 48 it takes 0, so it's 0. And so you have to remember that when we compute this, we're looking at the height of the subtree, so the height of 45 is 1, even though the balance factor of 45 is -1.
Even though we put 0 for that one?
So yes, because this is the balance factor for 45, which looks at, so first of all, it says what is the height of its left child, no left child, -1, minus the height of its right child, and the height of 48 is 0. And so that's where it gets -1 as its balance factor, but that's not its height.
Just say, why is it 0 if it take like 1 leg to get to it?
Right. And so the important thing to remember is the balance factor and the height are not the same, though the balance factor uses the height in its computation. And so, that can get a little bit confusing at times. And when we start to code this, honestly, it's a little bit better in code than it is kind of diagrammed out here, because it's just easier to see like what needs to be done as you insert the node. But don't worry, if this seems kind of a little bit not that intuitive, or you're uncertain about it, even after this lecture, that's okay. I would expect that. I just kind of want you to get warmed up to the idea of computing these balance factors and thinking about how the tree can be altered to make it more balanced. And we will continue in more detail with this and really get a grasp on all of the possible cases that we have to handle. And I think that also makes it a lot easier because there are a finite number of configurations that exist that have to be fixed. So in this case, we've got a problem at 50, right? Because it's got a 2 here. And that has happened after we've inserted 48. So we need to balance that. And so this is where we will do what we'll call a right-left double rotation. And so I guess a week from now, I'll summarize kind of these different rotations for you so that you have a nice list of like what they're called, because sometimes they do get different names, which is also unfortunate. But the important thing is that this is a different rotation from being just a right rotation or a left rotation. And so what we need to do is do that on node 50 here. And so looking at how this actually works, so if you think about how you can arrange these nodes so that they're balanced, it's not quite as simple as just kind of picking up one and changing it. Here we're actually doing this kind of compound rotation to make it a balanced subtree in this case. So before the rotation, before the right-left rotation, we have it looking like this in the tree. And then afterwards, we're going to have it looking like this. And so, as you can imagine, we can use a combination of like these metrics for computing, like the balance factor, the height, to determine what kind of rotation we do in code. And it's not, so I know like right now we're just kind of going through and you're seeing, you don't know if there are 100 of these different possibilities or, 5 of them. And I think it comes down to being like 4-ish, some edge cases or something. But when we do the coding part of this and implementing this, you'll get a firmer grasp on why we do a certain rotation in a certain case. But for now, just to kind of know that the idea is that we're rotating these in different ways overall to get there. So if we look at this, here are the steps kind of broken down. So before the right-left rotation, we have the structure that we had in the tree. And then if we look at it after we can do a right rotation, which will end up with that structure. And then, well, after the left rotation, we end up with this. And so it kind of breaks it down. It's a lot easier to see when we're actually like building a tree. Okay. So let's continue on with this same tree. So it was like this, and then we've balanced it, and now we're inserting another node. So we've got 80 and 75 here. And we can see that when we compute the balance factors for this, now we have 70 as being kind of the one that's out of balance, where we need to do a rotation to restore that balance. And so in this case, we'll do a left-right double rotation at node 70. And so we can, and kind of just to give you like a little advanced idea of this, the way that we're determining that that's the kind of rotation we're going to do is based on these, the balance factor here and here. So that is how we will like code this. It will be pretty much conditional based on these balance factors. So we're going to pull kind of this part of the tree that's 70, 80, 75, this part down here. We're going to work with it for a second. So this is it before the left-right rotation, and then after the steps of that rotation. And so you can see we end up with this structure here, which is a valid binary search tree, subtree of the overall tree, which we can then put into place here. We compute the balance factors. We'll see that everything is where we want it to be there. So that's what I want you to kind of just have an idea about. We'll get into more next week. The idea is that the trees, binary search tree, is only useful to us. It's only better when we can maintain balance. And there are many ways to maintain balance. AVL trees, the AVL method of balancing trees is how we will do that. And on Monday, we will start to code that and get an idea of exactly what that looks like. I know these examples can be a little bit daunting when we're rotating things in multiple ways and kind of not able to see it all at once. But just going to keep in mind that that's what we'll be doing. It's essentially just a swapping operation, moving pointers around, and we'll start going through that on Monday. We will not have class on Wednesday. I hope you have a wonderful fall break, and please return on Monday.